Okay, now let's consider acid-base equilibria. So, as an example, let's say we have a 0.01 molar solution of the weak acid HF, and let's find the pH. So we have to do our little chemistry, knowing that if we have a weak acid in water, that it will react to produce H3O plus and its conjugate base. So HF is an acid, it's a proton donor. It donates a proton to water, which then in turn produces the H3O plus ion and the resultant F minus ion. We can write the equilibrium expression in terms of K sub A, leaving the concentration of water out now. Okay, so what we've been given is a starting concentration of the acid HF. If we can find K sub A in a table somewhere, or have it given, we can determine the concentration at equilibrium for every species in the reaction. So we'll look up the value of Ka in a table, and we find it's 3.5 times 10 to the minus 4. Now for equilibrium problems, the first step is to define an extent of reaction. So in this case, we'll let X be the amount of HF that reacts. So at equilibrium, the concentration of HF will be the starting concentration, in our case 0.01 molar, minus the amount that reacts. The concentration of fluorine minus will be equal to X, and the concentration of H3O plus will also be X, just like the equilibrium problems that we have worked before. Now substituting these values into the Ka expression, I'll have X times X over 0.01 minus X. So now I just have a quadratic expression that I can solve for X. So X squared plus K sub AX minus 0.01 K sub A equals 0. Using the quadratic formula, I'll get two values for X. One value will be negative 0.0021, and the other value will be 0.0017. So since X is equal to the amount of H3O plus and F minus, it cannot be negative. And so only the positive root of X is physically meaningful. Therefore, X, which is equal to the H3O plus concentration, is equal to 0.0017. So now the pH is equal to the negative log of the H3O plus concentration, which equals 2.8. So that's how we can use equilibrium to solve for the pH and the equilibrium concentrations of each species in the reaction.